Hi, this is Dr. Bernstin again with episode 3 of Dr. Bernstin's Diabetes University. And today we're going to talk about some basic science that you should know in order to understand the following sessions that we will be coming to on other occasions. We're going to talk about the insulin receptor, and we have a diagram, a cartoon for you to see what I'm talking about. The cells of the human body can arbitrarily be broken down into two types: those that require insulin for the entry of glucose, and those that can be flooded with glucose even in the absence of insulin. Those that can be flooded with glucose account for a small percentage of the weight of the body. They include nerve cells, the lens of the eye, cells that line small blood vessels called pericytes, cells in the kidney called mesangial cells, and possibly a few other cell types, but they don't amount to much in the way of mass. Now, it happens that the cells that I just mentioned, because they allow glucose to enter in the absence of insulin, get loaded with glucose in diabetics who have high blood sugars, and these cells are frequently the first to be damaged by elevated blood sugars. Now, the bulk of the mass of the body is made up of fat cells, muscle cells, and organs made up of organ cells. That's the bulk of your weight. Therefore, since these tissues make up the bulk of your weight, they're great dumping grounds for glucose. If your blood sugar is high and you make insulin or you inject insulin, that insulin is going to put glucose into these cells that make up the bulk of the mass of your body. As I said, muscle, fat, and organs. Now, I want to show you how this happens because we're going to be talking about it again with other sessions. In the illustration, you'll see toward the upper right corner something sticking through the cell membrane. I might point out that the cell membrane goes around the entire cell. It's called a phospholipid bilayer. And we see the insulin receptor with a pocket in the top, and there's an orange ball in that pocket. That pocket has the right shape and electric charge to grab an insulin molecule that may be floating around in the bloodstream. Now, I don't know how many insulin receptors there are on a typical cell. I've read articles about insulin receptors. Some articles say there's one receptor per cell, and I don't believe this. Some say there's 1 million receptors per cell, and I don't believe that. Some say that there are 100 receptors per cell. That sounds sort of reasonable to me, but nowhere have I seen an authoritative statement of how many receptors there are per cell. So we're going to look at this one receptor and assume that there are a number of them. The insulin lands in that pocket, and you see what looks like two bananas. Those are lengthy protein molecules. So the receptor is symmetrical and is duplicate, has two long, skinny protein molecules that are called, I believe, an alpha chain and a beta chain. And when insulin lands there, the electron bonds between the carbon atoms in those chains start jiggling around. You don't have to know what electron bonds are. They just connect one carbon atom to another, and proteins are made up of chains of carbon atoms. When these electron bonds get jiggled around, something happens at the tip of the receptor. An amino acid called tyrosine, which is present at the tip of the receptor, picks up a high-energy phosphate group called ATP from the cytoplasm of the cell, from the interior of the cell. And when the tyrosine gets phosphorylated, as it says on the diagram, there is a chain reaction where energy moves across the cell. And you see all these steps in the chain reaction moving across the center of the diagram with arrows. And energy is transported in this chain reaction, and it gets to the vicinity of the two bubbles in the left part of the diagram. These big bubbles have the same phospholipid bilayer as the actual cell does. And they are storage vesicles, storage bubbles, for additional protein molecules, namely those circular things that look like cored apples. Those are glucose transporters. They're the glucose transporter of human fat and muscle and organs, and are called GLUT4 because they were the fourth glucose transporters to be discovered. Other similar transporters were discovered in animals before they discovered them in humans. Now, not shown in the diagram are the railroad tracks that transport materials throughout the cell. They're called, these tracks make up the cytoskeleton or cell skeleton, and this cell is crisscrossed with railroad tracks, and like the tracks that trains roll on, they have bumps on them. The energy that got transported to the vicinity of these vesicles or bubbles ends up activating a molecule called dynein. Dynein works in a fashion very similar to the picture we're going to show you next, which is a picture of kinesin 1. Dynein is going to drag these storage vesicles or bubbles to the surface of the cell. And it works like kinesin 1, but I don't have a picture of dynein, so I have to show you the picture of kinesin 1. And in this picture, it looks like a funny-looking horse or bug, and at the top, at the very top, there's a legend that says cargo, and there's a glob of something which could be a glucose transporter, and you may notice that there are 4 legs at the bottom of this creature, and they're walking on the cytoskeleton of the cell from one bump to another. Those bumps are a chemical called myosin, and this dynein is going to drag the bubble to the surface. And there are a number of dynein molecules getting energy, as we just saw, and dragging these bubbles to the surface of the cell, where the bubbles merge with the surface of the cell, just like a soap bubble would. And when they merge, as you can see in the diagram, they leave the glucose transporters behind. And in the diagram, you see these glucose transporters actively pulling glucose into the cell from the bloodstream. Later on, after the glucose transporters get tired out, the kinesin 1 molecule comes along and brings them back into the interior of the cell, where they're stored in new vesicles and recharged. So there's dynein bringing them to the surface, kinesin 1 bringing them back in, and both these motor molecules are actually walking on the cytoskeleton of the cell. And this all took place because insulin landed in the receptor, as illustrated in the diagram. Please get my book, Dr. Bernstein's Diabetes Solution. It's available at virtually every internet bookstore and many local bookstores. It contains much more information than these lectures that I'm giving you, and really is essential if you want to keep your blood sugars normal, as I do.